Welcome to STEM Talk.
STEM Talk. STEM Talk. STEM Talk. STEM Talk. STEM Talk.
Welcome to STEM Talk, where we introduce you to fascinating people who passionately inhabit the scientific and technical frontiers of our society.
Hi, I'm your host, Dawn Cornegas, and joining me to introduce today's podcast is the man behind the curtain, Dr. Ken Ford, IHMC's director and chairman of the double secret selection committee that selects all the guests who appear on STEM Talk.
Hi, Don. Great to be here.
So today we have our friend Dr. Mark Shelhamer on the show, and Mark is a professor at the Johns Hopkins School of Medicine and the director of the school's Human Spaceflight Lab. Previously, he served as chief scientist of NASA's Human Research Program, and he was serving in this capacity when we met him, actually. In addition to his work with NASA, Mark is an advisor to the commercial and consumer spaceflight industry. In today's interview, we talked to Mark about some of this work, as well as the research that he conducted on the first all-civilian crew that successfully orbited the Earth for 3 days. We mostly talked to Mark, however, about how the harsh conditions of space imperil humans and how he is investigating ways to maintain the health and also the performance of astronauts on a long-duration spaceflight. We also discussed how the lessons that Mark is learning about human spaceflight can be applied to human healthcare back here on Earth.
Before we get to our interview with Mark, however, we have some housekeeping to take care of. First, we really appreciate all of you who have subscribed to STEM Talk, and we are especially appreciative of all the wonderful 5-star reviews.
As always, the Double Secret Selection Committee has been continually and carefully reviewing iTunes, Google, Stitcher, and other podcast apps for the wittiest and most lavishly praise-filled reviews to read on STEM Talk. If you hear your review read on STEM Talk, just contact us at stemtalk@ihmc.us to claim your official STEM Talk t-shirt.
Today, our winning review was posted by someone who goes by the moniker Writer3765. The review is titled, Very Interesting. It reads, I love listening to educational podcasts, but also get bored easily. This podcast kept me interested, engaged, and I learned information that's actually relevant to my life.
Well, thank you, and that's awesome to hear, Writer3765. And thanks to all of our other STEM Talk listeners who've helped STEM Talk become such a great success.
Okay, and now on to today's interview with Dr. Mark Shelhamer.
STEM Talk. STEM Talk.
STEM Talk. STEM Talk.
Hi, welcome to STEM Talk. I'm your host, Dawn Cornegas, and joining us today is Mark Shelhamer. Mark, welcome to the podcast.
Thank you. Been looking forward to this.
Absolutely. And also joining us is Ken Ford.
Hello, Don, and hello, Mark.
So, Mark, just to get started, you grew up in the Philadelphia suburbs back in the 70s. So, first question for you is, what kind of kid were you?
Well, I described myself, I guess, as a typical nerdy kid. Maybe that's overstating it, but I was good at science and math in school. Well, I was good at most subjects, frankly. I was a good student, but I was definitely math and science oriented. And I guess maybe the typical way of putting that is I was certainly more comfortable with things than people, let's say, at least at that age. Not that I was a loner or, but I was kind of geeky. I like the science kind of stuff. So in my later years, it was a revelation how interesting people could be when you combined them with that.
Well, I'm guessing you couldn't have been too geeky in school because you played drums in a band. Is that right?
I played in a band in high school, in a high school band, the school bands.
In a high school band.
Yeah, exactly. The marching band, the concert band, the jazz band. But I guess the non-nerdy aspect would be the jazz band, which was frankly a world-class jazz band in our high school.
Wow. I understand that you had an uncle that played a really key role in fostering your interest in math and science and related fields.
That's correct. I had my Uncle Stanley, and he was married, but they did not have any kids. So they would bond with many of us as their nieces and nephews. And he lived in northeastern Pennsylvania. I lived in southeast Pennsylvania, but we would see him frequently. And one of the smartest people I knew, I would say, even though he was not highly educated, he was really very bright, had been a surveyor in the coal mines in northeast Pennsylvania for a while and then did some other things. So definitely he was attuned to math and things, but he was like the cool uncle, and he made it then cool to be interested in science and math and really just took an interest in us and our interests. And I was able to have conversations with him. I'll say one of the things, going back and talking about seeing how interesting people can be, I made a deliberate decision in my later years through graduate school and definitely afterwards to nurture independent relationships with some of my relatives who I only kind of knew through my parents, right? You go visit your relatives and you know them because your parents know them. But I really took a deliberate effort to get to know some of my aunts and uncles, including this one. So I would spend a lot of time with him just sitting and sharing a glass of bourbon and talking for hours about stuff. And that was, he's long since dead, but that is time that I do not consider wasted. Really very enjoyable.
When you were only 10 years old, I hear that you took up an interest as a hobby in electronics. Is that right? And what kind of electronics were you most interested in?
Yeah. So as far as I can tell, it was when I was about 10 years old. And it was a gift. It was a Radio Shack 50-in-1 electronics kit. I see Ken indicating some recognition. Very popular. You can find them on eBay. And matter of fact, I did find one on eBay. So I reproduced that. Yeah. And as far as I can figure out, it is that same uncle who gave me the gift, or at least recommended to my parents that I get it. However that family arrangement thing works out, but at least his name was on the gift when I got it. And I was just fascinated by the fact that you could take this little wooden box with these electronic components in it that you could rewire springs and wires and make stuff, including radios. So I'm sitting in the living room. This would be in the early 70s, and back before the internet and all this other stuff, which made all this stuff a commodity. But the idea that I could wire up in just a few minutes a little radio and just throw an antenna wire up over a lampshade and sit there and listen to radio broadcasts coming from hundreds, if not thousands of miles away with something that I just built, that's magic. And it's still magic to me.
Yeah. And those Radio Shack kits, Radio Shack was not like people understand it now. Even the name gives you a clue, right? Radio Shack, not radio store, right?
That's right.
It was sort of a collection of nerds would go there, and you could buy all sorts of kits and all kinds of things where you couldn't really find most places. And there also was a thing, I don't know if you were into it, called Heath Kit. Remember Heath Kits?
Remember them. I have the Heath Kit was my first ham radio, my first amateur radio that I built. My parents were very generous, and an aunt of mine, and I still have it. It's in a family house in northeastern Pennsylvania. I also have a small assortment of unbuilt Heath kits that I have amassed over the years. Those are rare. They're becoming hard to find.
And some of the Heath Kit stuff was really high quality.
Yep.
There was an amplifier. I can't remember what it was a copy of, essentially, but it was quite good, an amplifier for stereos.
Yeah, maybe it was a Macintosh clone or something.
It was a clone
like
of
that.
something, a power amplifier, but it was quite good.
Yeah. I learned a lot by building those. And then, of course, since you built it, you can fix it. And that's very empowering.
That's awesome. So, Mark, after graduating from high school, you enrolled at Drexel University, which isn't that far from where you grew up. And your plan was to become an electrical engineer. But at some point in school, you changed your mind. So what happened? What drove that change?
Yeah, so I thought I was interested in, of course, computers, radios, electronics. I thought I would do something like computer engineering, design computers, or maybe power electronics was an interesting thing because how do you make transistors, which inherently have small active areas? How do you build them so that they can pump enough electrons through to do high currents and high voltages? That kind of thing interested me. But my father had a rather minor heart attack, fortunately, at that time when I was a freshman in college. And my mother was a nurse for a long time. She worked into her 70s as a neonatal intensive care nurse. I had two aunts who were nurses, so this kind of medical background was infused to some extent. And my father had a pacemaker implanted shortly after that. So the idea of biomedical technology that was, in some sense, keeping him alive interested me, and I thought that would be a very interesting way to go. So I became more interested in biomedical engineering than electrical engineering per se. But biomedical did grow out of electrical engineering originally. The first biomedical engineers were electrical engineers.
Now it's an unusual and in some ways fascinating topic, but sort of unusual hybrid, right? The departments are full of people with quite a broad range of backgrounds.
Yeah, as it should be, because As you know, one of my things is the fact that you can't just look at one system by itself. So if you're going to look at what looks nominally like an electrical engineering solution to some biomedical issue, you better think about how the fluid flows and the bloods and things like that.
Right. And those topics are normally stovepiped into different people, different departments, sometimes even different schools.
Absolutely. You're talking my language now. That drives me crazy.
So you were at Drexel, and then after Drexel, you went to MIT. Could you talk about that transition and what the motivations and how you selected MIT?
Yeah, I remember it clearly because I was thinking about what I wanted to do for graduate work. I was interested, because of my electronics and radio background, I was interested in what we call signals and systems. How do systems process signals? How do radios process signals that they pick out of the air and amplify them and process them and demodulate them so that you can hear them? And digital signal processing was becoming a thing right around then in the mid-'70s. So I was really interested in signals and systems, professionally, control systems, communication systems. But I was also building up a huge hobby interest in human spaceflight. And I don't exactly know why. Certainly the shuttle program was starting up. 1981 was the first flight. And so I just became fascinated, just tangentially, but as a nerdy kid interested in technological things, became fascinated by human spaceflight. And I wanted to learn everything that I could possibly find out about Mercury, Gemini, and Apollo programs, starting in the early 60s through the 70s, the moon landings. And the more I learned about them, the more fascinated I became about them, that they were just what NASA was able to accomplish with technology of that era to be able to land on the moon. It just blew me away. And the more I learned about it, the more I realized just how audacious it became and how unbelievable it was and how unbelievably successful. So when I was looking for graduate schools, I was looking at places that were doing things like pacemaker design. How do you design the proper signals to deliver a pacing pulse to the heart without damaging it over the course of time, many years that you might have this implanted? Those kinds of things, which are still fascinating and interested me. But I ran across an advertisement description for a laboratory at MIT. It was at that time called the Manned Vehicle Laboratory, and has since changed its name to the Human Systems Laboratory. But this is a laboratory run by, at the time and for many years, Larry Young, who turned out to be my thesis advisor. And their thing was looking at how the brain processes signals from the different sensory systems, vision, the vestibular system, which I didn't know anything about at the time, the balance system, kinesthetic and proprioceptive systems, how the brain processes signals from those systems to make a coherent sense of orientation, among other things, and how that processing changes when you send people into space. So how do astronauts' brains process these signals, and what happens when they adapt to space flights? I had never thought that there would be a way to combine my avocation and my vocational interest, and so I had to go there.
Yeah, that makes perfect sense. And going there and working with him must have been a real turning point for you, and that really had you focused then on sensory motor effects.
Yeah. That was a huge change for me because, like I said before that, it was really looking at how computers and electronic systems, artificial systems, process signals of various kinds. And this was actually looking at how the human brain does it. So that was a whole new thing for me.
Absolutely. And so after you finished up at MIT, could you tell us about the transition and how did you end up at Johns Hopkins? Is there a story there?
There's a bit of a story. The space flight, when I was at MIT, fascinating and obviously a phenomenal education at a place like MIT, and especially under somebody like Larry Young. Chuck Oman was also the assistant director there. Just brilliant people that exposed me to a lot of things and really in some ways taught me how to think. But the space flight work that we were doing was very much applied work, addressing issues like space motion sickness and postural instability after people get back from extended duration space flight. And so I realized after a number of years doing that and looking at very much mathematical modeling approaches to it, but but looking at the applied aspects of it, I realized that I could really use some more fundamental neurobiological background. Just how is it that the vestibular system is working? And the vestibular system has a very intimate connection to the control of eye movements. There are reflexive eye movements that are driven by the vestibular system when the head moves. And I realized that I wasn't getting the full story of that neurobiological background. So I completely set aside any spaceflight work for about 7 years and went to Johns Hopkins School of Medicine to work with some of the leading people in vestibular and oculomotor research. And my postdoc advisor was David Robinson, and I ended up working very closely with a neurologist there who worked very closely with David Robinson. His name was David Z, and he's still there working. And David Z and I we published, about 15 papers together on various aspects of this. But I really wanted to go to fill in what I thought were gaps in my knowledge about the fundamental neuroscience.
So, Mark, when you arrived at Johns Hopkins as a postdoc fellow, this is in 1990, you continued the research that you were doing at MIT on sensory motor physiology and modeling, and that included the astronaut adaptation to spaceflight when it comes to sensory motor adaptations. Can you give us an overview of this research and also its significance and how you tracked back into studying the astronaut population?
Yeah, so I was continuing some of the work that I had done at MIT, but like I said, it really took a direction away from spaceflight because Johns Hopkins was not doing human spaceflight research to any great extent at that time. That's since changed. So I was starting to look more at the fundamental aspects like what are the mechanisms that drive adaptation? How exactly is it that the brain changes sensory motor programs to accommodate changing circumstances? And that could be pathology, it could be aging, it could be changing the prescription of your glasses, which changes the magnification of the lenses, or it could be going into space. So in that sense, there's a connection between all of those. But the work at Johns Hopkins, at least initially, and even continuing now with my clinical colleagues there, really was oriented toward how this happens in patients with vestibular problems, patients with eye movement problems.
In 2007, you published a book titled Nonlinear Dynamics in Physiology, a State-Space Approach. The book provides mathematical computational tools that are used to analyze experimental data. Can you tell us about the book and its goals? This sounds fascinating.
Yeah, so around that time, early 90s or so, when I was a postdoc, not only was I interested in sensory motor systems and getting the background fundamental neurobiology and looking at adaptation on patients and normals, various sensory motor perturbations, I still wanted to continue the mathematical side of what I was doing. And there was a book that came out around this time. Actually, it was probably when I was still in the 80s when I was in graduate school, a book called Chaos by Gleich. And that was kind of put chaos, nonlinear dynamics thinking, put it on the map, made it approachable. And I remember a friend of mine, fellow student, Dan Murfeld, came into the lab one day and he had just read it. And he said, reading this book, I've become convinced that there's a lot that we are missing in our data when we analyze it, partly because we're not looking at variability in the data. We tend to think of things like engineers, means and variances and standard deviations. And we look at the mean and we think that the variance and the variability in the data is noise in the bad sense, in the sense that it's messing up the thing that you're actually trying to accomplish, which is the thing that's represented by the mean. And one of the points of nonlinear dynamics, which then became morphed into fractal physiology and those types of things, is that variability is really important. And variability can be meaningful, and especially variability in human movement. Variability in life means that the thing is living and exploring and engaging with the environment. And when you get rid of variability, that's a bad thing. So that had an influence on me, that reading that book. And then I started to read more and more things and started to publish a few papers looking at variability in eye movements and vestibularly driven eye movements and visually driven eye movements, and analyzing those signals from the point of view of nonlinear dynamics. So I wrote some papers in that area as well around that time and started teaching a seminar course at Johns Hopkins every other year or so for a couple of years. And then I was contacted by a publisher, World Scientific, and they asked if I would like to, I don't know how they found me, but they asked if I would like to turn my course syllabus into a book, which I then did.
That has to be a very interesting topic. When you look at human physiology, there's all kinds of opportunities to understand it in a dynamic systems approach.
Yeah, absolutely.
Very interesting.
Right. Right. And the idea of engaging variability explicitly and not just wishing it away, that's, and as a signal processing person, that also had great appeal to me. That variability is telling us something.
Absolutely. Sometimes it is the story.
Mm-hmm.
As you've mentioned earlier in our discussion, you've done quite a bit of work into motion sickness and related issues from a vestibular perspective. More recently, you've been working on space motion sickness, I understand it. Is that right? And can you tell us a little bit about that phenomenon?
Yeah, part of my work is devoted to space motion sickness. There's lots of people who are interested in space motion sickness and lots of people working on it. Space motion sickness paid my way through graduate school because the space lab experiments on space shuttle crews that we were doing in the laboratory at MIT at that time were to a great extent devoted to looking at causes, consequences, mitigations for space motion sickness. Made some progress through that time. It is still, space motion sickness is still a problem in professional astronauts and in private astronauts on private commercial space flights. So this is a problem that has not been solved. For a long time, NASA took a much more pragmatic position, which is that if you are going to be on a space station mission for 3 months or 6 months, nominally now they're 6 months, and you're suffering from space motion sickness for 3 days, what's the big deal? We'll just put you in your room or tape you to the wall or whatever it is and get you out of the way, get your sickness over with. We just won't plan any demanding tasks for you for those first few days. And that's not a bad solution in an operational setting. That was not a viable solution in the 1980s when space shuttle flights were only 1 or 2 weeks long. And if you're sick for 3 days, that's a huge impact on productivity. So that's, like I said, why NASA was so interested in it in the 80s, but then became less of a priority. Now that the Artemis program is ramping up and going back to the moon, it's now taken on some renewed interest. And also there's the post-flight problem of the converse of space motion sickness, which is the sickness that astronauts get when they return back to Earth's gravity, and especially if they are landing in a capsule in the water and the sea state is not calm. So then there's the egress problem when people may be sick at the same time that they are readapting to Earth's gravity. To some extent, all of the work on the vestibular system, sensory motor, adaptation, and astronauts is relevant to space motion sickness. That work has been reinvigorated over the past couple of years by a project that I had selected to fly on a couple of, 3 now, private space flights, starting with Inspiration 4, which was in September of 2021. And this was 4 people who went up on a SpaceX spacecraft, did not go to the space station, but were in orbit for a few days. And they did some biomedical experiments, including one that I have that was related to space motion sickness and seeing if we could develop a predictive test for space motion sickness to say which people might be more susceptible than others, not with the intention of saying who can and cannot fly, but with the idea of saying we might want to temper your expectations, or if you're the person who's likely to get sick, maybe we're not going to give you the most demanding tasks, or we're not going to put you near the emergency exit. And maybe we'll do some mitigations before you fly, like maybe doing parabolic flights or something like that. So yeah, that line of research is reinvigorated to some extent because I just happen to have, because of NASA support from 10 years ago or so, a simple procedure with simple apparatus that could get at assessing one of the contributors. There are many contributors to space motion sickness, but one of the contributors we think is vestibular asymmetry and asymmetry in the vestibular systems between the right and the left ears, and my project specifically looks at that. So I was in the right place at the right time when the funding agency, TRISH, the Translational Research Institute for Space Health, decided to fund some biomedical experiments on these flights.
That's awesome. So, Mark, kind of stepping back to some of the discussion we were having earlier about multidisciplinary research, on your Wikipedia page, you've got a Wikipedia page, there's a reference to your pioneering work on a multidisciplinary approach to human spaceflight research. So can you give us an overview of this work and your approach in that aspect?
Yeah, that is one of the things that really fascinates me is the fact that it becomes very acute and very recognizable when you send people into space, because the hallmark of spaceflight is that there are multiple simultaneous interacting stressors going on all together, and you can't pretend that they're not all there at the same time. So you've got altered gravity, typically 0G when you're in space. You've got isolation and confinement. You've got distance from Earth. Distance from Earth is not that much on a low Earth orbit mission, but it'll become dramatic on a moon mission and certainly a Mars mission. You've got the possibility of a toxic or hazardous environment if things start growing in the water supply or on the walls. And you've got space radiation, which is a little bit more harsh than terrestrial radiation. And those things are all going on at the same time. They're impacting probably every system in the body. So the body is adapting to these assaults, these insults, these stressors, and sometimes in very logical ways, in ways that you would expect. In other words, if you are no longer loading the bones chronically by being in a gravity environment, the bones start to lose calcium because you don't need to maintain that level of bone density, mineral density, and strength. So that's a perfectly natural, normal, well-intentioned adaptive process. But it's bad when you come back to Earth and you need the bone strength. So that's going on at the same time. There are changes in just about every other body system. And yet, these tend to be studied and addressed by different groups looking at different aspects. And you could, to some extent, ignore the interactions if you have the luxury of studying them independently and applying one stressor at a time, like we do in laboratory research on Earth. But when you go into space, like I said, they're all happening at the same time. And you can't ignore the fact that these things interact. So an example that I often give is elevated CO2. Elevated carbon dioxide level, which is prominent in a spacecraft because it is expensive in terms of resources, power, consumables of various kinds. It's expensive to scrub it down, to scrub it out of the atmosphere. And Scott Kelly, in his book, talks about elevated CO2 levels. He spent a year in space on the space station. And elevated CO2 has well-recognized consequences. It can make people irritable, lethargic, a number of other things. It's just generally not good for you. But some of the other things that are related to CO2, for example, there's a tendency to, if not pull calcium out of the bones, at least keep it from going back into the bones, to use calcium to buffer the acidity that comes from elevated CO2, increased blood acidity. Well, you've already got a bone demineralization problem because you're not loading the bones by gravity. So those are going to potentially exacerbate each other. The other thing the body does is, if the blood is not carrying as much oxygen as it used to because of elevated CO2 in the atmosphere, it can increase cerebral perfusion, the amount of blood going to the head. Well, you have a fluid shift issue in space because there's no hydrostatic gradient. You don't have gravity tending to pull body fluids down to the lower body, to the torso and the legs. So you've got elevated fluid in the head around the brain already. The last thing you want to do is send more blood to address the elevated CO2. And yet, these problems, CO2, bone, and fluid shift, tend to be studied by different groups looking at different things. And it's the interaction of these things that, in the end, is going to be the real killer.
Mm-hmm. Well, Mark, that's a great answer. And just as you just described, spaceflight has widespread effects on many different body systems at the same time during spaceflight. And you've been an advocate for developing approaches to examining all these different interactions in a very rigorous way. And just by the way, that's one of the first conversations that I think you and I had, was talking about how to pursue this in a more multidisciplinary approach. And we'll talk more about this a little bit later. But do you think, and I'm going to assume the answer is yes, but don't you think that we should also be taking this rigorous multidisciplinary approach and applying it to terrestrial medicine as well?
We absolutely should be. Now, that's easier said than done, but yeah, definitely. I'm engaged in what at the moment are just conversations, but rather detailed conversations with a couple of colleagues. I guess I can say names, Gary Riccio and Bill Queel, about addressing this very problem. There weren't by far not the only ones who are aware of this, but it's no surprise that there is let's call it a crisis in medical care in this country, certainly in primary care. And part of what I think is the crisis, there's access to care, of course, is an issue, but also, even if you have good access to care, there's the concern that if you have a complicated problem, you'll be assigned to a series of specialists who are all very dedicated and really good at what they do. But it's not clear that the specialists integrate their care. They don't necessarily talk to each other. And hopefully you have a primary care provider who will integrate all this information and make sure you're not getting things from the individual specialists that conflict with each other. But it's not only that, it's the fact that also somebody should be looking at things that clearly are medically related. We'll call them systems medicine issues, which is not just the integration of the different medical specialties and the different physiological systems, but how are things going at home? How are things in your job? Do you have a reason to live? In other words, if you have a debilitating illness, do you really want to get better? Is there something driving you to get better? What is that? If, in fact, you have an illness or an injury that's going to prevent you from doing things that you did before that gave you satisfaction in life, are there other things that can take their place? Can you rearrange your life? Sometimes literally rearranging your living quarters, your work environment, but also do you need to modify your peer group so that you have people who can encourage you to live a healthy lifestyle? Those types of things. All of those need to be incorporated into a systems medicine approach for medical care. And I will venture to say that it is the rare physician who thinks that broadly.
Especially the specialists and the subspecialists, I find. And you've raised an issue that's really, really important, sort of taking a systems view and having somebody doing the integration on behalf of the patient. They're not equipped. The patient's not equipped to do this. And this is so important and so rarely done.
Yeah. And it's easy for me to sit here and say this because I don't have to do it. But I'm in full recognition of the fact that each of these specialists has his or her hands full just becoming a specialist in their field. I'm not trivializing subject matter expertise at all. I'm saying it's perfectly understandable why this problem is there. But somebody should take charge of the system. We need to apply the same rigor that we do to the individual systems to the integration of the systems.
I was just going to say that. I think it would require a shift in how we educate primary care physicians and the specialists to interact with them.
Right. There needs to be a shift there, and it needs to be given the same level of recognition that it is a legitimate intellectual and academic enterprise.
In some ways more complicated.
Yes.
Look at the interactions between these complex systems and then all of the interventions that the various specialties have done in an incompletely understood dynamic system, which is really the harder job in many ways.
Yeah. Yeah, I agree completely. But since it's so hard to make progress. And since it's so hard to make progress, then it's hard to get funding and it's hard to publish and it's hard to say, it's hard to demonstrate that you're actually doing anything. And so that becomes a vicious circle.
And with respect to funding, we've developed sort of a whack-a-mole model for research based around disease as opposed to both wellness, but also the interactions between all of these systems, including the interventions.
Exactly. So my friend Bill Queel will say that we do not have a healthcare system. We have a sick care system, and that should change.
Yeah, we say that here too. Well, speaking of all this, you've had some success. It might feel pretty limited, but you really have had some success convincing certain groups that they need to embrace a more multidisciplinary approach in terms of their research, at least. Can you talk about some of the progress you've had in this area? And it must feel good to see any progress in such a tough problem.
It is indeed good to see some progress, and you're right. All hope is not lost. One of the things that I have to keep in mind is that I think the real success here comes from the fact that I try to imbue in my students this way of looking at things. So if we have a research project, it might look like a research project that's studying phenomenon A, but we try to say, how can we at least bring in some little piece of phenomenon B? Can we just talk about that? Can we find one paper that connects those two things and just add one additional measurement to this so that we can say that we're making it multidisciplinary? Let's just start thinking in those terms of making every project into a cross-disciplinary project, whether the sponsor or anybody else wants it to be that way or not. So that's one thing. But I think that the real success story at the moment is a project that I'm involved with, a NASA project out of the Human Research Program. It's called CIPHER. So CIPHER is CIPHER. It's one of the better NASA acronyms because it's actually pronounceable, but it has some meaning to it. So CIPHER is the Complement of Integrated Protocols for Human Exploration Research, CIPHER. CIPHER is a flagship program of the Human Research Program. It is a major project, and the goal of CIPHER is to look across a number of disciplines. So CIPHER has, I think, 14 or maybe 15 component projects by an equal number of principal investigators, including international investigators, looking at aspects of the cardiovascular system, fluid shift consequences, bone loss, a number of things, and cognitive function as well, vestibular function, sensory motor function, looking at all those. But one of the component projects is a data integration project in which there will be at least one person in the world, one investigator, whose job it is to pull the data together from all of those other projects and integrate them and look at how within a given astronaut on a given mission of a certain duration, how these different systems interact in a longitudinal fashion and being proactive about the integration. Now, I happen to be the principal investigator of that integration project, so to me, this is a great success. But we're also, I have to say, this is much to NASA's credit because this is a really daunting thing to do because it makes the astronaut test subject identifiable because I'm getting data from from a given individual, and I have to know how long that person flew and what the previous flight experience was and a number of other things. So the data become very sensitive there, and we're also integrating it not only across those different body systems and psychological systems, but also integrating it with medical data that are par for the course for astronauts, and also what's called metadata, that is largely the environmental data that goes on. So as an example of the kinds of things that this will be addressing, it's not unusual in a spaceflight experiment that I might have astronauts performing my experiment, and I don't get to know if those astronaut test subjects have taken motion sickness medication, sleep medication, any kind of medication, because that's private medical data. Even if it impacts my experiment, I don't necessarily get to know that. Now, that thinking is starting to change, but still it's a pernicious problem. So in this case, we get to know the medical data and, like I said, the metadata. What's the CO2 level on the space station when they did this experiment? Did they undergo a sleep shift because there was a new crew coming on board or there was a cargo vehicle that was docking? Those kinds of things that are all important for understanding how these different body systems work. So I think that's a huge step forward.
Yes, absolutely, I'd say.
Well, Mark, I know we're really excited to hear that this research is moving forward. And I do understand that you have said, and this is a quote from you, if there's one thing I'm known for, it's for banging my head against the wall, trying to convince people to do integrative research. So we're curious, how many scars do you have on your forehead at this point?
Yeah, well, I'm not the only one. There's a small group of us, a little cabal that gets together once in a while and shares our stories about that, some from within NASA and some from without. But I'm not here to pick on NASA specifically. Like I said before, this is a common problem in biomedical research because it's not trivial by any means to know, to acquire a sufficient amount of knowledge about any body system. These things are really complicated. So one of the kinds of pushback that you will get is people will say something like this: how can you expect me to start to investigate how my system interacts with 5 other systems when there's so much that I don't understand about my system to start with? And when I start looking at the interactions, how am I going to know that those are due to a particular interaction or just inherent to my system on its own? They're not wrong. That is a legitimate question. One of the answers might be to say that you're never going to know everything there is to know about your system. It ain't going to happen. So why don't we start looking at the interactions with other systems? And by the way, there is an intellectually rigorous way to do that. It's not just a way of saying, these 2 systems interact and therefore we're giving up any kind of hope of a detailed understanding. We can do a detailed understanding of interactions. It would potentially look different than a detailed understanding of the individual system. There would be things like emergent properties, things that come out of the interactions that are unexpected. They only happen when there are interactions. But we need to look for those. The other thing is that the incentive structure this became very aware to me, very, very real to me when I spent some time at NASA, that the incentive structure for investigators is not well aligned with doing integrative cross-disciplinary research. People get promoted, get publications, get grants, get the recognition of their peers and colleagues, including their department chairs and other people who control resources, by diving deeply into specific things, because that's the coin of the realm. People recognize what success in that type of investigation looks like. And if you're going to go in and say, yes, I'm investigating system A, which is my system, but look how interesting these interactions are with the other systems. They're really complicated, so therefore I can't publish anything yet. And boy, nobody's really willing to fund that. But isn't it interesting? Well, the incentive structure isn't necessarily aligned to support things that are interesting.
Absolutely not. And one of the things that's often lost on the funders, and then as a consequence on the people in the community, is whenever you're looking at the interaction between 2 complex systems, and let's say your primary focus area is system A, and you've focused on that your whole career. But if you really deeply understood in a rigorous way the way you're describing the interaction, not only would you understand the interaction, but you would actually understand something that you could not have learned otherwise about system A, which had been your life's work. So I think in a lot of ways that's lost when you talk to, at least often when I'm in conversation with people who are, an authority on system A.
Yeah, that's true. Why is it that to speak euphemistically, why is it that my system has a port that plugs in to system B? I didn't know that was there. And look how that system changes the behavior of my system in a way that, by the way, I can understand that because I now know enough about my system. But I didn't realize there was this mechanism for this external force, external stimulus to be applied to it. I agree completely.
I think that's very interesting.
So, Mark, we're going to shift gears a little bit. I understand that you've become an informal expert on the history of NASA's early stages of human spaceflight. So can you tell us a little bit about that?
Yeah, so that goes back to what I was talking about before about when I was looking for graduate schools and just serendipitously, I guess, the shuttle program was starting up and I was getting very, very interested in the early U.S. space program and the Russian program, Soviet program as well, but mostly Mercury, Gemini, Apollo through Skylab. And completely informal. I would not say that I am a recognized authority on this. I've had occasion to run across people who really know this stuff inside out. John Charles, since deceased, chief scientist for the Human Research Program, shortly before I became the chief scientist there, put me to shame in his knowledge of this material. But I just became fascinated by it. So I would say that I'm maybe an informal authority on the early space program, and just because the technological achievement still fascinates me to this day. And like I said before, the more I learned about it, the more amazed I was that they could accomplish what they accomplished with the technology of the time. And if you look at, for example, one of the things that fascinates me, you can go and buy the Apollo mission reports. They're online, and then they're also on Amazon. You can buy them. They've been published in book form. And every one of those flights was, boy, they were really flying. They were really going by the skin of their teeth. In some cases, the near disaster at some point in almost, I would say in every flight. These were experimental flights, and yet they worked. People came back, and then 3 months later during Apollo, they'd fly the next one, and the next one, and the next one. Every one of these was an experiment. And I think to some extent, to NASA's detriment, they tend to downplay the risk and the danger of these things, which I think is unfortunate, because it's the danger and the risk that, to a great extent, makes it worth doing, right? Mm-hmm. That's what pushes the boundaries.
And it's harmful to the goals of the agency.
Right.
When I was at NASA in the 90s, we received an edict that we were to speak of human spaceflight as routine. That was the word, routine. None of these are routine. And we were supposed to talk about spaceports and try to make it sound like an airport and sort of routine. Both the political logic of that as well as just the honesty, I always found great fault with that.
Yeah, I agree. And I think there's potentially a bigger lesson there, which is if you're pushing the boundaries like that, but you're still successful, and you can't argue that Apollo was not successful, what is it about the system, the bigger system that was put into place? Not only the technology and the rockets, and of course they had a huge amount of money, large resources available, but what is it about how the system was constructed to allow the Apollo program to be successful, even in the face of, some cases, real disaster, and other cases, near disasters? So that goes to one of my other real interests, which is resilient systems. That was a resilient system. What made that a resilient system?
We actually studied that for a while at the NASA Advisory Council when Jack Schmidt was the chairman. And, the basic finding was it's morphed into such a different organization that it's very different. We had some of the very, very best and brightest people living in our country working on this, with exceptional funding, exceptional support from the president down, and teams of who were super passionate, really quite amazingly young people driving this. So if you look at the average age of the engineers working on Apollo, it was 30 years old. And there was a very strong meritocracy. There wasn't near the bureaucracy that we have now. And so a lot of lessons to be learned from how they did this. It wasn't that it was a small program. It was a huge program, but it was handled in a much less bureaucratic way with a lot more authority invested in people with deep technical expertise.
Yeah, certainly I would agree. And that's a really great point, because it also shows that the way that you set up the bureaucracy and the administration certainly impacts the ability to carry out a successful scientific, technical, and research program. You can't just pretend that the technology will save you if it's brilliant enough. You have to have fertile ground put up around it.
STEM Talk is an educational service of the Florida Institute for Human and Machine Cognition, a not-for-profit research organization investigating a broad range of topics aimed at understanding and extending human cognition, locomotion, health span, resilience, and performance.
we may be on the cusp of another exciting time with NASA's Artemis program and plans to return to the moon. And right now, only about 600 people have ever flown into space, and nearly all of them were astronauts who were supervised and trained by their respective governments. And 2 years ago, that changed, and we talked about this a little bit already, when a Falcon rocket operated by SpaceX sent the first all-civilian crew on a 3-day mission orbiting the Earth. And there were several research projects related to Inspiration 4 to this mission, and you were the principal investigator on one of those projects, which you mentioned a little bit earlier in this podcast. So, Mark, what can you tell us about your project, which I understand is part of a NASA-supported experiment that will test and study astronauts through the year 2033?
Okay, so let me go back a little while and give you the full story of this particular experiment, which I think is an interesting story because it ties together a number of different threads, and this story also has the advantage of being true, at least as far as I can remember it. This goes back maybe more than 10 years ago, I would say, when I was doing a set of parabolic flight experiments. So this is in the NASA, what was at the time, the NASA Vomit Comet that flies a parabolic trajectory, and you're in free fall, weightless, for about 20 to 25 seconds at a time, repeatedly. And we had an experiment that was looking at some aspects of eye movement control, how the eyes would respond to visual targets. And this involved getting inside a small, dark, essentially room container inside the plane so that you remove all the other visual cues, and looking at LED targets that move back and forth while measuring the eye movements. And like any good human behavior investigator, I wanted to be one of the subjects for my experiment first so that I could help work out the bugs and see if there were any anomalies. So I was under the shroud in the dark area of the aircraft doing this, and I noticed that when I was looking at some of the targets, I was having a hard time fusing the targets. That is, I would look to the left or to the right, and instead of seeing one LED target, one visual target, one red dot, I would see two, and they would diverge. One would be above the other. So I had vertical diplopia, double vision, and it would change when the gravity level changed, which was very interesting. And there's a lot going, just like when you send people into space, when you go into parabolic flight, there's a lot going on. I was on motion sickness medication, the gravity level's changing, so you get a little dehydrated, it's fatiguing, et cetera, et cetera. So who knows what the phenomenon is? So I thought maybe I was just tired or it's a side effect of the medication, until I mentioned it to one of my co-investigators who also performed the experiment, and he said, oh, I noticed that too. So if it's just one of us, it's an anomaly. If it's two of us, now it becomes science. So now we thought, well, this looks like a thing that we might want to investigate. So I happen to know about a set of studies that had been done by Charlie Markham and Shirley Diamond through the 80s, 90s, maybe even early 2000s, which then just seemed to disappear for some reason, where they were looking at a similar phenomenon in astronauts, not with vertical positioning of the eyes, but with torsional positioning of the eyes. That is how the eyes rotate about the line of sight. I don't want to get too technical about that, but they found some evidence that there was a relationship between torsional asymmetry, a misalignment of the two eyes in different gravity levels, and its relationship to space motion sickness. So it occurred to me that maybe the same phenomenon, which is a vestibular phenomenon, it's based on the vestibular system, maybe the same phenomenon is now manifest with changes in vertical positions of the two eyes when you change the gravity level. Maybe we should revisit this work by Markham and Diamond, incorporate not only torsional positions of the eyes, but vertical positions of the eyes, and figure out how to measure this in a non-invasive, rapid way that doesn't involve a lot of sophisticated instrumentation so that you could do it in space. So this became a NASA grant funded by the Human Research Program more than 10 years ago now, and I was the principal investigator on that. The idea there was that you would take something like an iPad, a tablet computer with you when you land on the moon or Mars, and you pull it out of the drawer and you do a little assessment test on yourself before you say, I'm ready to put my suit on and go out and start doing some work, as opposed to saying, I think I need to do a little bit of rehab here and get my sensory motor system back in order before I put the suit on because I don't want to fall down and break a bone. So that became a NASA project, which I had to turn over to my co-investigator, Michael Schubert, when I spent some time at NASA. And then it became Michael Schubert took this in separate directions, not only space flight oriented, but also started looking at clinical applications of this in subjects, military people who were exposed to blast injuries, which impact, because of the overpressure, impacts the vestibular system. And so he found some evidence for similar effects in that population. So it's gone in a clinical direction, looking at vestibular patients and people in military populations. But it was also there under NASA funding. It was selected as part of the CIPHER complement. We talked about CIPHER a little while ago. It's since morphed into something unrecognizable when it became incorporated into CIPHER, but that's okay. That's how science works. But in the meantime, the project was there. We had developed the tablet computer-based mechanism to make this assessment that we thought might be related to space motion sickness. So when Inspiration 4 started gearing up, this would be about 2 years ago now, and it became clear, thanks to the commander, Jared Isaacman, who has a real affinity for biomedical research because of his connection to St. Jude's Hospital, they were going to do biomedical experiments. And they coordinated some of those experiments with TRISH, the Translational Research Institute for Space Health in Houston. And TRISH reached out to a few investigators who they thought would have experiments that would be relevant, but also ready to go, wouldn't require a lot of prep time, experienced investigators. We could make this happen very quickly because the turnaround time for this was just a few months, whereas for a typical NASA flight experiment, it's several years. So that's how that happened. And I consider myself very fortunate to have been in the right place at the right time to take advantage of that.
Absolutely. That's often so critical. And it's important to not only be at the right place at the right time, but be prepared as you were to take advantage of that opportunity.
Right. There's another point that I wanted to make about that, and it's the reason why I went back to did the 15-year excursion about that, which is, I think it's worth noting, this was based on a serendipitous observation in parabolic flight by me and one of my co-investigators. It is very likely that if we had not been there performing our own experiment as subject matter experts, that this might not have been noticed, that a naive test subject might have had the same experience, but just thought it's part of the experiment, just not commented on it. So I want to make that point because this is why it's going to become more and more important for scientists to fly in space with their science, because so far astronauts are extraordinary people, of course, and they're very highly trained in all of the scientific investigations that they undertake when they go into space, but they're not experts on every one of those experiments like the principal investigators are. So who knows what we're going to find serendipitously when we start sending people whose job it is to just delve deeply into specific science areas into space.
I've heard this discussion before in the context of human issues related to human spaceflight. And I always thought that a good analog for that is NASA's experience with Apollo 17. So the only real scientist to walk on the moon was Jack Schmitt. And he had the exact right expertise for this. This was his expertise, his PhD expertise. And we learned more about the moon, in particular geological issues, on that one mission than all the others combined. And I think there is merit in having a real expert on the right mission at the right time. And that was a great example of that. He was not expected to ever fly. He was sort of training the other astronauts. And that's a wonderful thing. And he was training very talented and skilled people. But there's still a difference. And I'm very glad that he had the opportunity to fly.
Yeah, agree. I think if I recall correctly, the quote that appears in some of the books at the time was that it's easier to train pilots to pick up rocks than it is to train geologists to fly airplanes.
Mm-hmm.
Right. It all depends on the geologist.
It depends, of course. It depends
so
on the geologist.
It turns out that they
right.
trained him beautifully.
Absolutely.
But not all geologists would do well in that.
Right. But again, the point being that Apollo, even when they got to Apollo 17, the sixth landing, it's still an experimental spacecraft. And so let's not pretend that we can just swap a scientist in there willy-nilly. No, but it was an extraordinary scientist, of course.
Right.
Yeah.
And given that Apollo was a nationwide, all-of-nation effort, it's not surprising to me that in a large country, highly motivated to do this, all of the best people were interested in it. It's not hard to imagine that you could find a geologist that would excel as an astronaut in all aspects of being an astronaut with the right training.
Right. And what I think is going to be one of the great potential benefits, or will be a great benefit of private commercial astronauts, and especially with commercial space stations, non-government space stations, is the ability to send people up to just do their science like they do it in the laboratory here on Earth. Not highly programmed, tightly scheduled science, which tends to be what happens on ISS, and it's had extraordinary benefits, but it does not lend itself to tracking down serendipitous observations for just, if you've been in graduate school, you know what it's like. Let's just go in the lab and see what happens. Let's try this thing. And sometimes that's where the most interesting and useful things happen. Can't typically do that in spaceflight, at least not in the area of biological and human subjects research. Not yet.
Yeah. So, Mark, in 2013, and you've talked about this a little bit, you took leave from Johns Hopkins to serve as chief scientist of NASA's Human Research Program. And during that time, you specifically looked at the effects of space radiation on people, as well as the behavioral risks of being confined with a small group of people in very tight quarters on a long-duration space flight. And in describing this project, I read something where you said, and this is a quote from you, NASA wants to send people to the moon and Mars without killing them or them killing each other. And I just want to say that I love that. And it's true, isn't it? Especially the part about people killing each other. Can you talk a little bit about some of the behavioral risks associated with long-duration spaceflight?
Yeah, absolutely. So, of course, I'll give the disclaimer that that is not my specific area of expertise, but I did oversee it, and it was a real revelation to me, I'll have to say, coming from a biomedical engineering background, and especially a mathematically oriented background, and looking at the vestibular system and sensory motor behavior through mathematical models to a great extent, and just seeing a lot of things, even though being aware of the importance of interactions and the messiness of biology and physiology, still looking at things somewhat mechanistically and coming in and realizing that it's this somewhat squishy, qualitative aspect of psychological function, mood, motivation, interpersonal relationships, these kinds of things that and somewhere in the back of your mind, you think, maybe astronauts are just immune to those kinds of concerns. And astronauts are extraordinary people, but they are people. And something like a Mars mission is going to push things to the limits. I used to say, if I were giving a talk, look around the room, pick 3 or maybe 5. It would be either 4 or 6 people on a Mars mission, probably. But look around and pick your 3 best friends in the room, and everybody else leaves. But now you lock the doors and nobody gets in or out for 3 years. Are you still going to be best friends after 3 years? Now, you don't have to be best friends to go on a successful Mars mission, but you don't necessarily want to be enemies either. And you want to maintain mood, motivation, all of those other things, and you want to not be homesick. And all of these things have to be incorporated. And sometimes you would get pushback from astronauts and others saying that it's really not that big a deal. I mean, astronauts are astronauts. We eat stress for breakfast. This is what we do. We thrive on stress as astronauts. And it's true. They know how to temper stress and live in a stressful environment, no question. But even if you think you're tempering that stress behaviorally, you're not going to act out on the fact that your crewmate is driving you nuts. The stress can still take a toll physiologically on the immune system, on the gut microbiome, on the cardiovascular system, on a number of other things. And those could have effects which you can't separate from the other body systems. So this was a real change in my thinking about how seriously this has to be addressed. And the other thing that makes it difficult is that there is no good terrestrial analog for the situation of sending 4 or 6 people in a small spacecraft on a 3-year mission to Mars. You can look at submarines, right? Extended missions, maybe submerged for 6 months or so, but it's a fairly large number of people, and you can evacuate if you absolutely have to for a medical emergency or something like that. Wintering over in the Antarctic, that's pretty good. It's dangerous. It's isolated. It's not that confined, and there's a lot of people. NASA has analogs where they will lock people in a facility. High Seas is not a NASA analog per se, but in Hawaii is an analog where you can put people in for up to a year. They're isolated. They're confined. But they know they can get out if there's a real medical problem, so it doesn't have the danger.
That changes everything.
Changes everything.
And people have this idea that they'll be looking out the window and looking at all the pretty blue dot Earth. They're going to be seeing nothing. It's pitch black for almost all the time, percentage-wise.
Exactly.
And all the physiological stressors that you talked about too, from the multifaceted approach of research, just thinking about all those different things that are affecting you during spaceflight physiologically as well.
Right. So one of the things, this has an implication which puts me at odds with a lot of my colleagues in the area of artificial gravity, because artificial gravity, engineering-wise, not trivial, but it's certainly feasible to implement artificial gravity on something like a Mars mission. You don't have to spin the entire spacecraft. You can spin the sleeping quarters, for example, or a small part of the spacecraft, and it would address a lot of concerns: cardiovascular deconditioning, bone loss, et cetera, et cetera. We don't know how much artificial gravity you would need, for how long, what levels. But I look at it in a different way. Imagine yourself on a 9-month journey, which might be what it takes to get to Mars, on the way out, on the way back, 6 to 9 months, and you're away from Earth. You don't see the pale blue dot like you did before. Everything that you're familiar with, all the comforts of home, have gone away. Communication delay, which will be on the order of 20 minutes one way when you get to Mars, in the vicinity of Mars, means you're not going to be having conversations in any normal sense with people back on Earth. It's pretty austere and pretty demanding. And now you take away one of the only things that makes spaceflight unique and fun and interesting: weightlessness. Do you really want to do that to people? Maybe let them be weightless. Now, you don't have to do it chronically, like I said, but still, I think it's a psychological countermeasure, being weightless.
Yeah, I've heard this conversation once, and, I think you've hit the point clearly. You could just turn it off. Then the question is, what if you weren't able to restart it?
Mm-hmm.
Mechanical systems often object to being turned off.
Yep.
But it's a fascinating issue, and even that's been studied for decades, and there's always an engineering bugaboo that someone brings up. Typically, it's discussed in the context of spinning the whole thing, and I think that's where the problems arise. There are many, many problems associated with it, but if you just did the living quarters or just the sleeping quarters, you'd have a big benefit without all of the hundreds of objections that you get.
Correct. And it could be that you only need an hour a day at 0.1 G. That's the other thing. We have no idea what level of partial gravity would be needed to address these degradations in the physiological systems.
And that's something you'd want to know before you
Absolutely.
Sent people on the journey to Mars.
Right. But you can only do those experiments in space because on Earth you have that 1G bias all the time.
Right. So, Mark, naturally, most of the human research has been focused on keeping people healthy in space. And something that you're excited about is the potential of spaceflight research to help us enhance healthcare terrestrially, which we briefly discussed earlier. But not everyone sees the broader scientific value of human spaceflight research. And to address this, you and a group of your colleagues published a paper in 2020 titled Selected Discoveries from Human Research in Space That Are Relevant to Human Health on Earth. So, first, what are some of the reservations that people have about the ability of spaceflight research to enhance terrestrial healthcare? It seems like it would be pretty obvious.
Yeah, it's not completely obvious, I would say. I think there are some valid concerns. So you would say, if you wanted to take an adversarial position, that how is it relevant that studying a small group of highly selected, extremely fit individuals in a very unusual environment, being spaceflight, spacecraft, who are highly educated and highly motivated, meaning they are also very compliant, so they exercise all the time and eat right. How is the study of those people relevant to the rest of us on Earth? Is that really a generalizable population? And not only that, even on a good day, how many people are you going to have in any particular human spaceflight experiment? Maybe a big project will be 10 or 15 astronaut test subjects over a number of years, and there'll be a lot of logistical constraints on that experiment just because of the nature of doing human spaceflight research. And now compare that with a standard clinical trial on Earth that could have dozens, hundreds, thousands of people involved. So you can see what some of the complaints are, or some of the valid criticisms. One of the other things that I will sometimes hear from my well-meaning colleagues and friends is that if you did not send, you would not have to study what happens to people in space if you didn't send them to space in the first place. Meaning, why don't you just use all robotic missions? Well, okay, that's a different question that goes back to the serendipitous observation, the fact that you don't send people into space just to do scientific investigations. There are a lot of other reasons. I like one of them that came out of an MIT report a number of years ago that I think encapsulates it about as good as anything that I've seen. It expands the human experience. You kind of either buy into that or not. It's what we do as humans. But, okay, back to your basic point. Those are some of the critiques. And also people will sometimes point out that if you compare the scientific return, however you want to measure that, from human research experiments, human research in space, compared to astronomical research, astrophysics research, physical sciences research, it doesn't look so good sometimes. So one of the things I found, I happen to have a personal connection to people who work in with the Hubble Space Telescope. 10,000 papers, I think, is what I found most recently, published on HST, Hubble Space Telescope data. We don't have anything like that from human research in space. But that doesn't mean that what we have found is of no value. One of the things it means is that it's really hard to do this research in space. There's a huge number of confounds, and it's difficult to get a large population because we're just not flying a lot of people. So it's really hard.
And it's a mistake for advocates of human spaceflight to argue with critics who are measuring the value based on ridiculous criteria like number of papers. Only an academic would be this confused. The purpose of human spaceflight is not science. Science is one of the minor drivers for the nation when it thinks about, do we endure the risk and cost of human spaceflight? It's a driver, but it's a minor driver.
Yeah. Actually, I'm glad you put it that way because I prefer to put it this way. Instead of being criticized for, let's say, meager scientific return, this community should be applauded for being able to do any valuable science at all when you can consider the number of confounds that are involved in trying to do human research in space. It's a very highly uncontrolled situation, very much unlike a laboratory, and yet good science comes out of it. It's just very hard.
Mm-hmm. In the same 2020 paper we're discussing, you looked at 5 areas of physiology that support your contention that there are broader implications of spaceflight research. And I'd like you to walk through these 5 areas just quickly and discuss their potential relevance to scientific and medical issues here on Earth. Just hit each of the 5, if you don't mind. Bang, bang, bang.
Okay, so you may have to remind me of the 5 as we go down. But now, of course, I'll also give the disclaimer that each of my co-authors has a subject matter expert contributed their part of that paper. So I contributed, along with a co-investigator, Jacob Bloomberg, the vestibular sensory motor part, which was the last part. So let me start there. I think a couple of things come out of vestibular sensory motor research in space. The premise of the paper was that there are things that were found by doing this research in space that you would not have found by just doing it on Earth. There's something about the space setting, not saying, well, if we were clever enough, we would have found it on Earth. No, saying something that really the population or the change in gravity level, There was something fundamental about doing it in space that led to these results. But I would say one of them would be the recognition of the importance of vestibular asymmetry, which I talked about earlier. The fact that there probably is, even in normal individuals, a synaptic, neural, anatomical asymmetry, slight difference in the vestibular apparatus between the two ears. Normally compensated in a 1G environment, you don't see any manifestation of it until you change the gravity level, which means it has to be done in space. So that's probably one of them. The other one, bigger than that, is just the basic recognition of just how adaptable the sensory motor system is. If you can be born and raised, evolve, and develop in a gravity environment and go into a weightless 0G setting and in just a matter of a few days or weeks adjust to that and carry out productive work, that is an incredible adaptive capacity. So recognizing that adaptive capability of the human brain and human body is really one of the most important things. There's a part in there that talks about pulmonary function, so the lungs. There were some predictions about how perfusion and ventilation would interact. That is, how blood flow to the lungs and airflow into the lungs, how they are coupled to each other so that you get efficient transfer of oxygen from the air into the blood, and how that's matched in normal situations on Earth, but how it can be altered by the geometry of the lungs. And this was recognized dramatically, let's say, made acute when people went into space because the geometry of the lung changes when you go into space because gravity is not, I'll say, distorting it. It's not changing the shape of it. And this has implications for how you would treat various things like acute respiratory distress syndrome on Earth by how you position the patient. If you position the patient upright, gravity has a certain impact on the shape of the lung. If you position them supine versus prone, so face down versus face up, laying down, has an impact. And so these can all have clinical implications for you, how you would treat this syndrome. So that's another one of the things that came out of there. In terms of bone loss, we know that astronauts lose bone mineral density, calcium, from the bones, and they exercise rigorously and vigorously when they're in space, more or less 2 hours a day for nominally 6 days a week. And some of that is impact exercise, some is aerobic. And that's what it seems to take to deter a lot of the physiological deconditioning, including loss of bone mineral density, although it doesn't seem like it's a completely successful countermeasure. There's still some work to be done there. But what this helped people recognize is that there's a big difference between cortical bone, that is the bone on the outside of the bone, and trabecular bone, the kind of honeycomb structure that's inside the bone, which is what gives the bone its strength. And typically what's measured from astronauts over the years, this has been changing, but typically what had been measured in astronauts, because it's easier to measure and easier to see the effects of spaceflight, is the cortical bone. But the cortical bone seems to be somewhat the loss of cortical bone seems to be somewhat reversible, whereas it looks like the loss of the trabecular bone, the inside part that gives it its strength, once that's gone, it's gone. Doesn't seem to recover in astronauts when they come back to Earth. So if you've got an aging population that starts becoming sedentary or maybe is subject to bed rest for a medical condition, once they lose that bone, they've lost it. So you got to keep them from losing that bone to start with.
Mm-hmm. And the things that we tend to do, both on Earth and in space, really don't address that. I don't think we're serious, but if we were serious about things like Mars missions, we would be looking at pharmacological approaches that are off the table to even discuss seriously at this point.
Yeah, so exercise combined with bisphosphonates, which is an osteoporosis medication, were used in spaceflight.
I wasn't thinking of that. So, the bisphosphates, as you know, have a lot of downsides. The fracture rate doesn't change much, but you do a lot better on your DEXA scan.
Yep.
I was thinking of things like growth hormone.
Right.
So that the normal function of the bone continues.
Yeah. So in general, for countermeasures in spaceflight, at least my point of view is, and I think I'm not the only one, you would want to avoid pharmaceuticals as much as possible because you don't know the long-term side effects. And certainly you don't know how, in many cases, how the metabolism of those pharmaceuticals may change when people go into space because things change, including the microbiome.
But the relative risk in a Mars mission to the human is immense.
Yeah.
The risk associated with some of these pharmacological interventions are vanishingly small. We worry about what happens 30 years from now. These people will have a spectacularly good chance of not living to complete the mission. And this is why I think they won't happen anytime soon. The risk is really big.
It's true. The calculation has to change dramatically. And at some point, this becomes really acute when you start talking about the radiation risk and the very likely increased likelihood of lifetime cancer after a long-duration space flight, especially outside of low Earth orbit.
Perfect example.
Right. And you could say, well, okay, you have a vastly increased likelihood now of getting cancer, but you walked on Mars.
Exactly.
So, is that a fair trade-off?
They would all raise their hand.
Of course. But as a society, right, now you bring the ethicists in, which you should, because now it's a societal decision, not an individual decision. But the other part of that calculation is to say, well, that's okay, fine, that's a separate category. What about the more immediate potential impacts of radiation like a solar flare, solar particle event that might have immediate and detrimental impacts on cognitive function?
You may not complete the mission.
You may not complete the mission. So that's a different calculation.
Yeah. That's why what I'm saying. These risk calculations and the relative benefit need to be rethought, I think, once you're dealing with anything close to Mars.
Agreed. Yeah. You have to really start saying, we're here to carry out a mission, and the mission comes first, and the primary role of the mission is not necessarily to keep me, the astronaut, happy and healthy. That'd be nice, but there's more to it than that.
Exactly. Your health is not the primary consideration.
Absolutely. If it is, don't go.
Yeah, you're in the wrong business.
That's right.
Yeah.
So following up on Mars, NASA estimates, as we discussed earlier, that it'll take 6 to 9 months to get there, probably 7 or 8, I would guess. And that really requires very good planetary alignment. We won't get into it here, but there's a certain alignment that is optimal for transition. And, right now NASA said that it's planning to send humans to Mars in the 2030s. By saying 2030s, that gives you a whole decade, but I think that should be taken with a huge grain of salt, perhaps all the salt you have in your house. That said, let's, for the sake of conversation, suspend disbelief. So, could you give us your thoughts about a future Mars mission, in particular, though, not about the mission overall, but the role that human research might play in really enabling this mission? And we've been talking about this now all throughout this discussion. But if we could briefly just hit on the key sort of barriers, we hit some of them already, but we could rehash them real quickly for the listener.
Yeah, okay. So let me start with what I'll say is the conventional answer, which does not mean trivial, and I'm not disparaging that answer. But like I said, just every body system is impacted. So are you going to have artificial gravity? How much? Are you going to have to deal with psychological issues? Things as simple as homesickness and how that impacts the ability of people to get along. Elevated CO2 levels or not, possibly altered sleep schedules because of altered light-dark cycles. All of these things going on, interacting with each other. Potentially, there are reasonable mitigations for every one of them individually. That doesn't mean that they're easy. That doesn't mean that we're there yet. But you can at least imagine a countermeasure for just about every one of those systems, at least the more critical ones. But as I've alluded to a number of times, the thing that really is a concern to me is when these things start interacting and when you have 5 different systems that you believe you have mitigated properly, independently, when they all interact with each other in some crazy way that you have not seen before because you've never sent people to Mars before. You've never put a small number of people in a confined setting like this and sent them that far away from Earth for that long a period of time. And one of the things that's, I think, little recognized about human spaceflight is that every time there is a more ambitious set of missions, so going from Mercury to Gemini to Apollo, Skylab, Space Shuttle, there seems to be another type of medical or physiological problem that comes up. So, for example, we didn't see orthostatic intolerance, right, fainting or potential fainting, until the longer flights of the Mercury program. We didn't see space motion sickness until the Apollo program, when the spacecraft was big enough for astronauts to start moving around and making a lot of head movements in space. We didn't see the visual impairment problem, what NASA now calls SANS, spaceflight-associated neuroocular syndrome. This is a change in visual acuity that happens over extended spaceflight, we think, due to fluid shifts over an extended period of time. Didn't really see those, at least didn't get attention until longer flights on the space station. Didn't see until just a few years ago deep vein thrombosis, a blood clot in the jugular vein, which is potentially fatal, on an ISS mission, which was found, by the way, during a research study, not during a medical test. So that was a lucky find. So how is it that every time there's another type of mission, something else happens that we didn't see before? We need to do better at this and not just address the problems that we know we have, because if you mitigate all of the known problems, the thing that's going to come up and kill you is the thing that you haven't mitigated, the thing that you haven't thought of, and that could be a whole new phenomenon. That's unlikely. We know a lot about physiology and physics of extended spaceflight. My contention is that it would be some crazy interaction that you have not considered between these different systems and between those systems and the unusual circumstances of a Mars mission. So tracking interactions, I think, is going to be the thing that's going to have to take up larger precedence. And that means in the research side, before people fly, but I think it also means monitoring, appropriate level of monitoring during the flight itself, so that you can see, why is it now that the CO2 level is up and I'm not seeing the reactions of the crew that I normally see in a space flight? Something about those interconnections now has changed.
Mark, not only is this an exciting time for you in terms of your NASA work, but you also have projects involving SpaceX and also Blue Origin. So I'm just guessing you must be pretty busy right now. Is that correct?
Yes, it's a very exciting time, not only the NASA projects, but also commercial spaceflight. We don't have anything definitely with Blue Origin yet, but we're in conversations with those. And the idea of reinvigorating the space motion sickness research for private astronauts, I think, is very exciting. We want to not only have their experience be pleasurable, but have them be able to do useful work when they go up, because eventually we hope to be sending scientists.
And Elon Musk has gone on the record as saying that SpaceX will land humans on Mars by 2026. We're curious what your take is on that statement.
Yes. Well, I'll say what I said in a podcast of a different venue several years ago. I forget who it was who said that you would, back in the days when newspapers were dominant, you would never pick an argument with somebody who buys ink by the barrel. Far be it from me to pick an argument with somebody who builds his own rockets. But I think that's Elon Musk has done and will continue to do amazing things. I don't think he's going to land people on Mars anytime soon, because of a number of things that we've discussed, including just the crazy interaction problems of human responses. It's really hard.
Just landing on Mars is very, very hard. For something as large as a human lander, the entry, descent, and landing problem is not solved. And I would bet him not doing that more strongly than the continuation of gravity. In other words, there is zero chance they're sending humans to Mars in 2026. Now, I wish him all the success in the world in every endeavor, but that's just not going to happen.
Yeah.
You couldn't get to the moon by 2026.
No, I agree. It's hard to overstate just how difficult a Mars mission is going to be. But, like I said, Elon Musk will continue to do amazing things.
He will, but he won't do that thing.
But he will not do that.
Yeah.
Now, following up on Don's recent question, I'm certain you don't have tons of free time. But when you do, I understand that you're still an avid fan of ham radio and that you still play the drums. Are these both true?
Both are true. correct. I have an entire room. My wife is very understanding in this basis. I have an entire room at home dedicated to electronics and radios of various kinds, which I use and repair and modify. And I have 2 sets of drums in the basement.
Mm. Well, hams are like that. Every good ham I know has like a ham cave, and it's full of things.
Yep.
And they typically have sort of strange-looking antennas hanging off their house and on a big platform behind the house. And they seem to have a lot of fun.
It's a lot of fun. And there's certainly the romance of radio, right? Picking these signals out of the air. Sometimes with what would, compared to what we have now, primitive equipment, I like restoring and using stuff from the 60s, 70s into the 80s. Just, remarkable what you can accomplish.
And it looked a lot cooler.
It looked a lot cooler, and you can fix it if it goes bad.
So, Mark, you've certainly had an amazing career. And in fact, your high school is so proud of what you've accomplished that last year you were inducted into your high school's inaugural Hall of Fame class. It's awesome. Just guessing that was an awesome experience for you.
That was an unexpected pleasure. I really enjoyed that. It was humbling. There were some people with some real accomplishments who were with me in that class of inductees. But my high school prepared me extremely well for college. It was demanding. The music program, I was talked about being in the bands. The music program, as my brother said when I was talking about this at one time, he said it was the first time that we as students were expected to work at an adult level, and that in the music program. So that made a big impact because that's very useful information. That's to know that you can work at that level. But also the music program, I'm belaboring the music program because this was when I spoke at the induction, I talked mostly about that. Not only that, but by playing music at that level, which at that high school is at a very high level, Pennsbury High School in Pennsylvania, Bucks County. By playing at that level, you knew what it took to play at that level. And you knew that you couldn't always do it because you just didn't practice or rehearse or whatever. So that you knew when you were faking it as well. That's a really valuable skill to have in any field, but especially in science. It's good. If you don't know the material, don't pretend. But you need to know that you don't know it.
So, Mark, just 2 other questions that are not science-based in any way, shape, or form. You mentioned earlier that, this one's a little bit science-based. You mentioned earlier that you have a good connection to the Hubble Research Program, and I've started often introducing you to other people that I know as one half of a power space research couple. And I'm just going to assume that the connection that you were referring to is your wife. Is that correct?
That is, in fact, correct. Yes, my wife, Jennifer Wiseman, is the chief scientist, senior project scientist for the Hubble Space Telescope.
That's awesome. And then one last question for you, Mark. There are dog people and then there are cat people. I hear you're a cat person, just like I am. So I'm going to ask, what are your cat's names?
Yes. Well, let's say that I'm actually ecumenical about this. I would say both a dog person and a cat person.
Yeah,
but,
same here.
Same here. But the cats were kind of a dowry. When I got married, my wife had 4 of them. So we had 4, and we had 4, not always the same 4, but we had 4 for a long, long time. But now I'm afraid we have 0. We lost our last one right before Thanksgiving of 2019. But the names of the first 2, I will tell you, because my wife is very clever about this. She was working at the NRAO, the National Radio Astronomy Observatory, and she had a position at the University of Virginia, where Thomas Jefferson had something to do with that. And so she named her first cats Monty and Cello.
Yeah, perfect. I like
Nice.
it.
I love
A
it.
little deconstruction.
There you go.
Well, Mark, it's been so fun talking to you today. Thank you so much for joining us on STEM Talk.
Thank you. It was great being here.
And thank you, Mark. It was really fun.
STEM Talk.
STEM Talk.
STEM Talk.
STEM Talk. STEM Talk.
Well, Ken, I just think Mark is amazing, and I always love talking to him. And this is indeed an exciting time for human spaceflight, which really may be at a crossroads.
As Mark discussed, spaceflight has widespread, often negative effects on the human body. Also, Mark is a tireless advocate for taking the biomedical lessons we learn in human spaceflight and applying those lessons to human healthcare here on Earth. There's much to be learned, and Mark is at the forefront of this effort.
Absolutely. And if you enjoyed this interview as much as Ken and I did, we invite you to visit the STEM Talk webpage where you can find the show notes for this and other episodes at stemtalk.us. This is Dawn Carnegie signing off for now.
And this is Ken Ford saying goodbye until we meet again on STEM Talk.
Thank you for listening to STEM Talk. We want this podcast to be discovered by others, so please take a minute to go to iTunes to rate the podcast and perhaps even write a review. More information about this and other episodes can be found at our website, stemtalk.us. There, you can also find more information about the guests we interview.